Okay, good morning, everybody. Thank you, Kaylin. A year ago, I stood in front of you all in Auckland and issued the community with an analysis challenge. And today, I'm pleased to announce the results of that challenge. So, first of all, for the benefit of those of you who are new to the community, welcome. The quick recap of the motivations behind the data challenge. Although microlensing has been observed for some time, there are still a number of outstanding challenges in the analysis and other aspects of the work. The challenge that always springs to mind is triple lens analysis, but there are other issues such as the classification, the distinguishing of binary lenses, binary sources, as Martin pointed out earlier, and other variable types. The analysis of multi-lens events has always been historically time-consuming, and with the advent of future expected data sets getting increasingly large, this has become a major problem. Although there has been major progress in this area in recent years, there is more work to be done. And the current software and process doesn't really scale to the size of the data set that we anticipate for WFIRST in particular. But going beyond that, we are currently, as you can see, a fairly small field, and we expect to be personnel limited. So our purpose was to attract more people into the field, but not just more people, but also a diverse range of expertise from mathematics, statistics, and informatics. Data challenges have been successful in a range of other fields in achieving these goals, and in particular in a range of other areas of exoplanets. And in particular, the radio velocity people most recently had a very successful challenge. So the goal of the first data challenge was effectively the zeroth-order problem. It was to take a sizable set of microlensing light curves and analyze them effectively and promptly. The first aspect of the challenge was, of course, to extract the parameter of the model accurately, but also to distinguish from variable stars based on a WFIRST-like cadence dataset where that is not necessarily obvious because of the peculiar cadence of those data. The goal was to encourage innovative approaches, and we took this into account in the evaluation of the challenge, and also to bring in new people. Matthew Penny have kindly offered to produce the simulated dataset on which the challenge was based, and I'll stress that only he had access to the actual input of that simulation throughout the challenge right up until after the submission deadline. The dataset consisted of 293 light curves in WFIRST filters both Z and W, and it consisted of 74 single lenses, including free-floating planet-type events, and a number of binary stars, including those of planetary ratios. It also included some cataclysmic variables, just to confuse you, but contrary to what some of the teams thought, there were no flat light curves. So just as an example of one of the simulated light curves, it deliberately represented the WFIRST cadence, but also the length of duration represented the seasons that we expect from WFIRST. And this introduced some issues because naturally some of the events were incomplete, and that causes some confusion. Entering the challenge, it was run and documented through the Microlensing Source website, which, if you haven't checked it out, is a resource for everything connected with microlensing. It also had a GitHub organization which was linked from that site, which provided the teams with a forum by which they can ask questions and post data. Each team was prepared a set of documents for the entry. The first consisted of their contact details, for my benefit, of course. Secondly, most importantly, they had a parameter table of all the fitted parameters for each of the models for every event and target in the dataset. But they were crucially also asked to provide a set of written documentation which described both the software they used, their fitting procedure, and the hardware. And this was actually proved to be more important in the evaluation stage than perhaps was originally thought. Optionally, they could provide graphical output such as plotted models and so on. 4 teams entered in the end, including 16 people in total, of which 7 of whom were effectively newcomers to the field and or students. All of the entries were anonymized for the purposes of judging, and even until right now, I am the only person who knows who entered. That was done deliberately to try and avoid any unconscious bias on the part of the panel. I chaired the panel, but I did not vote. The voting members of the panel are listed there, including both experts from microlensing itself, from computation and data reduction, and an invited expert on informatics and statistics. Both myself, Matthew, and the panel members were not allowed to interact with or advise the teams or participate in them. The GitHub forum provided a public forum for them to ask questions where necessary, and all of the answers were posed publicly as well. In comparing the challenge entries, obviously the one thing you can do with a parameter table is programmatically compare the answers provided by all of the teams with the original master table from the simulation. So I wrote some software to do that. I can't go through every plot and analysis for every team. Unfortunately, we will do that after the fact, but to give you a taste of what that analysis consists of, the first question, of course, is how accurately did they classify them? So I have prepared for the panel these comparison plots and the confusion plot on the right for in each case. They were provided with a table of the numerical documentation for all 290 odd light curves. Obviously, that was quite a lot to take in. So in addition to that, I did some analysis taking the difference of the original master table of parameters with those that were fitted in each case, and looked at the distributions of the difference from the original parameters. This naturally highlights some of the known weaknesses in microlensing, such as the degeneracies. For example, the U-naughts fitted tended to be slightly greater than the actual true values. That's something that we will return to at the end. The panel members were asked to evaluate each entry on account of 4 different categories. Firstly, of course, was the accuracy in how they modeled the parameters. Secondly was the overall process that they followed. And this was partly from the point of view of efficiency and scalability of the process to a large data set, but also incorporated things like how they handled the errors and analysis and so on. They were graded on their innovation, particularly because that's something we want to encourage, and also whether they broadened the field or brought in new expertise. Each of the teams will receive written feedback from the panel. This will describe their strengths and the weaknesses that the panel felt they had in their approach. They will also receive a copy of the analysis of the accuracy of their results. Some of these criteria are obviously important, but quite hard to evaluate. They're not something you can necessarily get from just a sheer analysis of the numerical parameters. And in particular, evaluating how efficient their software was or their process was is a true benchmarking system was not included in this particular challenge. We did think about it. The difficulty is, in order to do that properly, you really have to have consistent hardware, and for logistical reasons, that was not easy to do at the time. That is something that we may come back to in a future challenge. But for that reason, there was some subjective analysis for which the panel relied on the documentation provided. And in order to supplement that documentation, after the first round of judging, the panel decided they had some unanswered questions. And so I formulated a questionnaire which went out to all of the teams to get some consistent answers on all of the, specifically the hardware requirements and the processes used. I thought about giving you the team answers without the team names, but it didn't seem to make a whole lot of sense. So at this point, I'd like to stop and acknowledge everyone who took part in this challenge. Thank you very much. I know it was a great deal of work for you all. And with that in mind, here are the following grades. In the first category, in the accuracy of fitted parameters, there was some variation in how the different teams handle all of the challenge, not necessarily handling all of the light curves, but analyzing a subset. Overall, when the events were properly classified, the parameters could be accurately brought out, mindful of the known degeneracies and weaknesses in the modeling process. One area of work which is still ongoing is to handle those cases which were effectively unmodelable, for which all teams produced either nonsensical answers or couldn't accurately classify it. That's something that we will pick up at the end. The classification problem proved to be non-trivial. Actually, distinguishing the events proved to be more difficult than people possibly imagined it would be. In terms of software and efficiency of the processing, all of the teams used publicly available software, which was good to see. A couple of teams trialed some new approaches to the classification issue. This appeared to be in an early stage of development, but it was certainly good to see. There has been effective progress on the question of scalability, but further room for improvement is available. And it should be noted that this no longer really requires a massive computer cluster to achieve. At least 2 of the teams relied on laptops to do their analysis. As I mentioned, there has been investment in developing public and open source software for analysis generally. There is more work going on in that area, and there's some very welcome attempts to try some non-standard techniques, especially machine learning. This with evaluation had to depend strongly on the documentation provided, so I commend the teams to look carefully at the written return from the panel. And finally, in broadening the field, it was great to see that all but one of the teams included students and newcomers to microlensing. All the teams were led by people who were established in microlensing. So one thing that one of the lessons learned was there's more work to do to reach outside the existing community and bring in new people from different areas. So what's the next steps? The next steps is I have just as of last night received the final feedback from all of the panel members for all of the teams. So I hope to circulate that to all of the teams today. We are planning a paper describing the challenge and the lessons learned from it, which will be underway. I hope all of the teams who participated will join me in writing that paper. I encourage all of the teams to send me feedback on how they experienced the challenge, what challenges they found, what difficulties, what worked, what didn't. And there is some further analysis underway regarding what was difficult about the challenge, what we should learn, and what cases were particularly pathological in the results. And I also encourage all of the teams to publish separate papers for any particularly new or innovative areas of their analysis. Lastly, I'd like to point out that the GitHub repo will remain open and the dataset is there. So if you want to use it for the purposes of testing or training a machine learning system, whatever you want to do, the data is still up there. So in terms of lessons learned, the first is that we focused on processing a large data set with mindful of what we will face for W first. This was particularly difficult without benchmarking, as I mentioned earlier. We could do a benchmarking test if that is something the community thinks will be viable. This could be done at a limited duration workshop with a cloud-based server. That kind of drove some thinking towards doing future mini challenges, where maybe in conjunction with a meeting such as this, we have a specifically targeted hackathon for a limited period of time, we can rent some cloud-based computing resources and put a shorter duration challenge in the future. The other big lesson that I learned was actually reaching out beyond microlensing proved to be surprisingly difficult. I have had feedback that we definitely reached outside microlensing. People knew about the challenge, but getting involved does still seem to be difficult. I was comparing the results of this data challenge with that that is recently held by LSST, which used something called the Kaggle platform for data challenges. They got over 1,000 teams, most of which were actually non-astro. They came from mathematics, some from industry, some from the general public. This has some attractions. Obviously, it has great reach, and it would be that would bring in a lot of people. It has drawbacks in terms of cost. They do expect prizes. And we don't have that kind of funding. In fact, we don't have any funding. That's always an issue. It also does have a lot of high overheads. I spoke to the LSST team who ran that, and actually formatting the data in a format that will meet the requirements of the platform itself is a serious undertaking. It took them a very long time. And it's really designed specifically for supervised classification challenges and not necessarily for the sort of thing that we want to do. So there are pros and cons to that approach. This was sent to me by Gautam Narayan to illustrate the general number of teams participating as it corresponds to the prize money offered. And what they found is after a certain point, it actually doesn't really correlate, but having at least some prize money is kind of expected if you want to reach out. So that was one known issue. The next challenge up has been discussed among the microsit team, and it is felt particularly timely that we look at the data processing challenge. This is, as Rachel said earlier in the meeting, this is something that the microsit is actively working on right now, and extracting photometry from the WFIRST images is known to have some issues and some challenges. Of course, this will require simulating an image-based data set. That is a work in progress by the WFIRST not just the microsit, but the other science investigation teams as well. And for this reason, I'm not announcing the start of a new challenge yet. Watch this space. We hope it will be coming. We're making some progress in this sense of generating the necessary data, and we'll announce that in due course. However, as I mentioned earlier, we are considering doing a number of shorter duration mini challenges for specific concerns. So if you have any suggestions for a short duration challenge of maybe a day or two that we could work on, that would be the next direction to go. And I would like to wrap up by thanking everybody who took part. You did a fantastic amount of work, and also the members of the panel for whom they also had a lot of work, and Tiffany Meshkat at IPAC, who put together some really excellent documentation to try and help people get involved. Thank you.
All right, time for one quick question. Let's see, I saw your hand first.
Which one?
Use your seat mic, please.
Yanni, seat mic.
Okay, can you hear me now? Okay, so go back to the panel where you showed the grading, that one, okay. Broadening the field. So team 2, if I remember correctly, Valerio is on team 2. And I don't understand why the score was so low, because essentially all of the other programs, if I'm not mistaken, are using VBB lensing, which is the library that Valerio developed. So to me, I mean, it's like, that was the biggest influence, right? This is what enabled the other codes, right, to be developed. So I don't understand why the score was so low. So
this is something.
I mean, you're present in the decision. So if you can explain the thinking process behind why this was scored so low.
This was primarily graded on the number of people in the team and what backgrounds they came from. You make a good point. Yes, all of the public codes do, of course, rely on Valerio's library. That's something I'm afraid the panel didn't take into account in the discussion. Okay. However, it is acknowledged in the field that massive contribution that made.
Okay, all right, fair enough.
All right, in the interest of time, we should probably keep going. Rachel will be here for questions afterwards. Let's thank her again. I guess that WFIRST stickers would be very, very far to the left of the prize swag, so maybe nobody would use that. All right, the next talk is Etienne Bachelet from LCO, who's going to tell us a lot about Pylema, one of the new microlensing modeling tools.
All right, thanks, Kalen. So yeah, I'm Etienne Bachelet. I'm a postdoc at Las Cumbres Observatory. So today I'm going to present the status of development of Pylema, which is work done with a lot of collaborators. And so Pylema is the first open source microlensing software ever developed for microlensing. So give some context to my talk, I have to use a penny plot, so I did. So the very first is expected to be launched in 2025, and thanks to the works made by Matthew, we expect to find 1,500 planets along 30,000 events. And as you can see in this mass versus semi-major axis, W first will complete very well the work done originally by Kepler and ground-based transit and radial velocity detection, which cover very well the parameter space of, let's say, hot planet orbiting star at less than 1 AU. And thanks to this detection, we know a lot about this planet now, but the parameter space around cold planet is much less known. And it's because this primary method transit and radial velocity are less sensitive. But thankfully, microlensing is very sensitive to this region. So thanks to the very first, we should be able to understand much better this part of parameter space, which is very important for planet formation, for example. But one thing which is not in the plots of Matthew, maybe you can upgrade that, is also the very first gonna explore the planet population all along the galaxy, which is quite unique for microlensing. So that's gonna give us a lot of clue of the planet population all along the galaxy. But modeling 1,500 planets could be challenging. And one of some reasons are listed here. So for example, modeling is CPU or GPU intensive, and this is intrinsic to the microlensing magnification computation. So not much you can do about this. But also the degeneracies in the parameter space are quite important. For example, the closed wide degeneracy can cause some problem in the model recovery. And before 2017, there was no really open source code for the community, for newcomers, that they can plug their data in a code and have a fit very easily. So this was the motivation about creating this software in 2016. So in short, PyLima is fully open source. You can download it on GitHub, and I also encourage everyone to come and participate to the code, reporting issue, creating branch and things like this. For binary, it relies on the Python wrapper of VBB package, which we make a lot of effort last year to make it on GitHub and have a very robust Python wrapper. So for this effort, I would like to thank Fran Bartolich, Valerio Bozza, and Marcus Denmark for the help. Thanks a lot, guys. We tried to keep PyLima as Python-based as much as we could, and using standard scientific routine like NumPy, SciPy, AstroPy, Matplotlib, then which are very heavily tested. In the new version I updated some weeks ago, we implement a lot of Python multi-threading into the code, and we are working to make it more MPI friendly because the upgrade breaks some MPI implementation, so we are working on that. Since the beginning, we tried to use kind of professional software techniques such as BAPE8, online unit tests, automatic documentation with things, so all of the code is or should be well documented. We spend a lot of time to write examples that everyone can download and play to try to understand and use the code as for their wish. And of course, we spend a lot of time to test it on simulated and real events. And one of the first original ideas we have when we created this code was this transparent black box approach, in a sense that it should be a black box. If newcomers in the field of microlensing have some data, but it doesn't know that much about microlensing theory, can still download the code, plug his data or her data, and then just press enter basically, and this should be a reliable fit that you can use for a publication. So this is a black box part. But it should be transparent in the sense that you can, if you're interested, you can read every function and it's not hidden behind the scene, and you can really understand how it works kind of easily. Okay, so some example now. So we implement, of course, point source point length, final source point length, and variable point length. So here is this example of Augur 17651. The baseline variation was probably due to a variable blend because the variation, the amplitude of variation decreased with the magnification. So you can do that with PyLima. Yesterday we see a lot of talks about black hole candidates, so I decided I will put one in my presentation. I know the true name is not Ogle 19, it's a metro, but I forget the name, so I'm sorry about that. So this is a very strong black hole candidate. So to do so, you just use a point source point length, and you have automatically annual parallax orbital motion and Xarab if you need. So here we found this value for the fit. You can also have double source point length and double final source point length, which seems to be important according to Martin talk on Monday. So this is the same event. And of course, we implement limb darkening, binary ends, uniform binary ends, and point source binary ends, which can be enough if you have a very strong binary deviation. So in this example, this is a binary from 2015, where we have to fit the binary deviation on the top, parallax for the ground, but also parallax for Kepler, that you can see here in yellow and red. And so if you have data coming from a spacecraft, PyLima downloads the ephemeris on GPL automatically, so and then you can compute the parallax for this spaceship. So we have various fitting capabilities. So if you have good guess on your model, you can use the gradient method. But if you are more interested to exploring the global parameter space, we rely on differential evolution right now, which is implemented in SciPy. And thanks to the 1.2 SciPy that appears 1 week ago, I think, it now supports multithreading. So you should be able to go very fast on that. If you are more interested in posterior distribution, you can explore MCMC around your minimum using the awesome EMC package, which also supports multithreading in the version 3.0. And we are working to make it MPI friendly. We have some issue right now, but should be doable quickly. And we have some green method if you're interested to use that. So you can also simulate event. So for example, here it's a kind of a planetary event that WFOS can see. So we use that to simulate and fit WFOS light curve during the saga in 2017, where students were trained to play with WFOS data. But we also use it to simulate the Romeria strategy for our key project. And of course, we use it also to make some fitting tests. So to give some example, this year we work on this Ogle 2011-417 puzzle, which was originally published by Shineta in 2012. And this beautiful binary deviation was originally published as a close-by binary. And in fact, thanks to the model prediction, we found that the period was about 1.4 years with a kind of strong radial velocity signal. So because the lens was closed, we expected to be able to measure it. And so Boiseta in 2015, they took 10 spectrum on the VLT, but they didn't find any variation, as you can see on this dot, which was in very strong contradiction with the Microlensing prediction that you can see in black here. So there was this big tension going on. So we decided, okay, let's try to remodel that with PyLima. And we found a competitive model, which is represented here, which is explained by a 2 times more distant and 2 times more massive binary lens. And in this new model, the period is about at least 10 years, so it's not very surprising that Boiseta didn't measure any signal from their spectrum. We also published this 232 binary event. So the mass is still remain unknown, but it could be potentially a brown dwarf candidate. And what was interesting in this event, it occurs during full moon, so the follow-up of the caustic deviation was difficult. And also this event was highly blended with G about 50. So this creates some issue in the modeling, but we find something consistent. And thanks to Gaia, we were able to assess that the blend is actually not the lens. It's OB15232. Okay, so now we are really happy to see that people in the field begin to use our code to make their study. So as I said before, we really encourage people to join the effort, and everyone is welcome to help us. So here is a list of papers in preparation. So far I didn't explain the acronym for PyLima, so it stands for Python Light Curve Identification and Microlensing Analysis. So I speak about the later, but not really about the light curve identification. It is because it was not implemented yet in PyLima, but since 2 years, we work with a student at Las Cumbres Observatory to develop a light curve classifier, in a sense like you have a big photometric survey and you are interested to find microlensing. This kind of challenging to find the needle in the haystack. So we developed this machine learning approach to do so. So we begin to use it, for example, in ZTF, which releases alerts through the Mars system that you can find at LCO website. And you can see the prediction of this code with the time of the light curve. And at some point, our classifier thinks this could be a microlensing candidate. So these works were mainly done by Daniel Godinez. It's, of course, fully public. So we're going to implement that soon. And in short, this software works with computing like 40 or 45 statistical metric of each light curve, like the skewness, the kurtosis, the von Neumann ratio. There is 40. I forget about everything. Then you ingest all of that in a random forest algorithm. You train it, and it should give you a relevant answer. And note that this code is flexible enough you can use it in every survey that you have. So we have a paper that should have been submitted when I write the talk, but I think it will be only tomorrow or something. Anyway, but we have a poster outside if you are more interested to discuss about that. So I think I'm run out of time, so I'll just leave it here and take questions.
Great. Questions for Etienne? Radek, saw your hand first.
Planned approach of this is a black box and you just need to add data and then push one button to get good fit or publishable fit. Does it work for binary lenses?
That's a good question. I think we are in the stage that we can say that it works pretty good if, in this way, if you have good coverage of the event.
What pretty good means in percent?
Like you need good coverage of the caustic entry and the caustic structure, basically.
Jen?
Could you comment a little more on 417 and why you found a new model? Did you find the old model and then this model was better? Or what kind of degeneracies did you encounter?
So we on microlensing in this room know there is this closed wide degeneracy. So originally when I took this event, it was to test my orbital motion codes, and then I explored the closed and wide parameters separately. So in the closed regime, I refound the same model as Ingu in 2012. But surprisingly, I found this wide model kind of fitting better as a first order. And so I say, well, okay, maybe that can explain everything. And then we make this analysis, and we found that actually the wide model give a very different mass and distance and things like this. So that explains different orbit, and so yeah. Well.
Is it also preferred in say chi-square?
Yeah. If you
two models solutions, I think he cannot because our model and his model uses different normalization scheme, so it's difficult to say which one is better. But because that event has a very strong high order effect, so from the initial preliminary grid search, I think we missed the wide solution, and he found the wide solution.
Matt?
The ZTF alert stream processing is really important. Are you planning on making an alert service for microlenses so that we don't have to figure out what's going on with the millions of events per week or whatever it is?
So let me ensure I understand well your question. So first of all, every ZTF alert are public, right?
Too many.
What?
Too many.
Yeah, so we have a first broker in LCO that you can sort. So we use that as a pre-filter, and then we ingest it in this machine learning stuff. And it is expected that when we have something that works properly, we can release alert to the community, yes.
Yeah, I think that's really important.
Great, let's thank Etienne again for great work. Next up, we have Marcus Hundertmark from Heidelberg, and he's going to tell us more about Pylema.
Hopefully I will do that. Yes. So, good morning, everyone, and thanks very much for the introduction, and thanks very much to Etienne for providing us with Pylema, which is a true asset in the earlier months. And where's the clicker? Here we go. And I'm going to talk a little bit about the well-informed user side of Pylema and what we've learned in the course of the W1st Data Challenge. And a few things that I prepared when not knowing how we actually did in the challenge. So it will be in some of the statements might be obsolete now. So the basic motivation is that W1st reminds us really, and the data challenge, how unusual that unusual parameter combinations and models will clearly appear in the data set, and we better get ready to figure them out. And also that we should prepare ourselves not only for the modeling itself, but also to be as complete and to catch as many events as possible in their parameters in order to assess what the planet occurrence rate is, including the multiplicity at various levels. So the multiplicity of the lens, the multiplicity of the source, and multiplicity of, well, multiple planetary systems, of course. So for preparing that, and we devised a slightly different strategy. And before I come to that, I just asked the more, well, rhetoric question if we are affected by a publication or a selection bias, and that is clearly the case. And this is also something that W1st will greatly help us with. So if you're having a look on the position of microlensing source and lens stars, then and take that from the NASA's Exoplanet Archive, we see that most of the sources are still located and reported and assumed to be at 8 kiloparsecs, while there seems to be an overabundance of closer planets. And we know, of course, that in some of these we are using a galactic model to assess the distance, so it is not a fair representation. So if we would reproduce these planets based on what we found, we would just end up with a galactic model or the mix of galactic models that have led to the discovery. So in that sense, it will be very interesting to see what kind W1st of statistics W1st will offer us. Also because it's will be a next step from the Spitze program we've also heard before, which nicely included that. So rare events are intrinsically important. So rare is beautiful in a Shannon entropy sense. So if you're looking at the planets again and the planet semi-major axis, this deceptively suggests it's a linear scale, but actually it's a logarithmic scale. And you're putting in a kernel density map. And you look at what is the most unusual event that is there, just blindly, not looking up what you think is interesting, then the most unusual event in that context would have been that event. Well, Radek knows that event. If you're looking at the title, you realize, yes, it is an unusual event because he dubbed it a circumprimary, so a triple lens model. So it is good to think about what is there, but also we know from the structure of our events there are certain regions and islands which are there. But when you're going to the cinema and come back, sometimes you are not happy with the ending. So, and you go to the YouTube channel, how it should have ended. And then you are getting a response that is much closer to what you like. In our case, it's also, in order to assess what is there, we need to assess the detection sensitivity and to figure out what really is there, not only what we detect. So if we simulate that, and I'll talk about how we do that currently a little bit later, the planet mass function and the planet mass ratio function can be reported on, of course, per planet and perhaps per single star. And there's still a point in reporting a PMF and for the theoreticians, but also because you can combine that with more insights from a galactic model. So while the PMRF is a bit more stable, that's more closer to our heart because it is something we are getting from our FITs. So if we are usually reporting this in a log S, log Q space, so the separation between the binary events and a factor Q, and this is usually simulated by injecting planets in, for instance, a survey, and then extracting these maps, which is a fairly time-consuming procedure, as those of you who tried that before have figured out. So, and we are looking for ways of getting and overcoming that issue here with Pylema and a slightly modified approach. So I'm afraid, Eric, yeah, we define it as a detection criterion quite often, something which comes with a delta chi-square and something that usually comes with some Gaussian assumed noise, but that there's no reason not to improve these things and to make it more flexible. In our case, the multiplicity, when we're simulating events, we factor in a multiplicity, a linear law in log space where a 0.1 solar mass system has a 0.1 has a 10% chance or 10% multiplicity fraction, and a 10 solar mass star has usually a 80% multiplicity fraction. And so you can, when simulating these events, correct for that. And that is also something which limits our understanding of the sensitivity map. So 10%-ish, well, uncertainty on what is actually there. So the traditional approach is to that we've used most of the time for RoboNet is to determine the sensitivity. For that purpose, we inject planets all over the lens plane for a given point source, point length model, which is one. And for the binary ones, you have to replace them, insert them, as Suzuki did it in his work, for instance. And then you can assess where the areas are that we can detect here in log relative deviation. So the green and red areas are well detectable. And traditionally, we then calculate the detection zone based on that. And that also initially, with the envelope of that, you can already find in Golden Loop 1992, motivating also the high magnification events. And later in the RoboNet team, the Horn et al. Paper 2009 gives you a good idea of that. So and unfortunately, this is for one mass ratio, so you have to repeat that time and again in order to reach the desired solution. You can also get something out of it because each of these detected planets comes with a topology assessment, and it also comes with a close White binary assessment. And from that, you can conclude that, of course, what you would have expected, which parts and which images belong to a certain category, which can be useful when you're preparing your fit. So the detection zone Monte Carlo we've devised gets rid of the issue that we have to simulate many, many maps, but instead we are putting a planet somewhere based on a proposal function that can be a simple rejection sampling scheme at a certain place in the lens scheme. Then we determine what are the closest images to that, and we check if these depart by a certain threshold. If that's the case, then we do the refit and analysis where Paylima is so helpful because it enables you to decide if it's there or if it's not. So especially for large data sets such as WFirst, you just want to inject a couple of those in a large, well-sampled data set to get an idea what's going on. And that should make an assessment of the sensitivity for large data sets viable. So how does that help Paylima? This might be the question here. And so in that case, I just want to highlight one aspect that the light curves really need also a good initial boundary condition. And we're using the differential evolution algorithm as a workhorse. And if you simulate such an event here, some more intermediate topology close to, well, nearly close, in order to figure that out and how to probe the parameter space, the differential evolution heuristically probes the parameter space, and that gives us something. Already on the walk, and these are plenty of samples and ideas where your local optimum is located here in log S, log Q, and alpha space, so you can see where your best solution is. It also highlights where potential degeneracies are. They are not necessarily converged in these overdense regions, but they are potential candidates to be probed. So we thought that's a good approach. So how does that? Also, we combine it not in a one integrated package, but in two steps with the SciPDE and the EMC package. You can also use the output of the differential evolution in order to inform your Markov chain Monte Carlo to get things faster. And in that respect, this is not part of the standard package. You will have a better performance on that. But the final part should be dedicated, of my talk should be dedicated to the to triple lens models. And this is another case where you're having a degenerate mapping. The E population is plotted here in log S1 and Q1, just for illustrative purposes. And you can see that you get multiple and probe the degeneracy space of a triple lens model. And while we are preparing and waiting for VBB end, which will continue these and we were not a little bit impatient. So our master student, Kai Nicholas, was working on simulating that and calculating the coefficients again for the triple lens model and revisiting it. And the usual thing is sometimes you have structures like these where you really don't believe, and we were validating, and the initial validation is not complete. And so validating that model is also challenging because probing everything can take quite a bit of time. So what it is, the PSTL model is part of Pylima now. It's a purely Python-based package. It's rather slow for the time being. We're solving the 10th order polynomial and the coefficients nicely summarized by Ree in 2002. And the idea was go back, contrary to the suggestion of Ree, use computer algebra systems and figure out if they can optimize it in a way that the coefficients to be calculated can be calculated in a very efficient way so that you have as little overhead in time as it needs to be. And it turns out, in addition to the traditional Mathematica or the even older Maxima packages, we also tried the SymP, which turned out to be the so far best possibility for n-lens systems, and for us at least. But I suppose Valerio has also a point on that, and he will talk about that later. Sorry. What I wanted to say is this is now one of our point source triple lens potential events that is an artificial light curve. And if you throw the binary modeling, so try a binary fit with Pylima, then you will easily see that you cannot reproduce all the features that are shown here. And the PSTL model as it is seems to work, and we've tested that in a couple of events. By definition, as long as you're not on a caustic crossing, it's more likely to do a good job. But as I said, this is only to bridge the little gap, and that was also motivated by the W1st challenge. Unfortunately, as it turned out, there was no triple lens inside of that. So let me conclude quickly. We found a way to enable assessing the planet detection sensitivity in a more efficient way. And we can estimate and resimulate things thanks to Pylima much more efficiently, have a temporary PSTL model at hand, and we would like to take the opportunity at the end to encourage, where is the team, Matthew, to provide, here we go, a simulated PMF for the challenge, because recovering that and your inserted PMF would be very valuable at the end as part of the challenge. Thank you for that.
Great. Time for one quick question from Marcus. Han?
This is not a question, it's a comment. I circulated the data set of one triple lensing event. It's a multi-planet.
Use your seat mic, please.
Data set was handed to him.
Can you use your chair mic? Han?
Oh, sorry.
Okay.
Yeah. And then, in 2 days, he provided a solution, exactly the same solution as I got. So his code, even it is still point source, triple lensing code, it works very well.
Fortunately, it was not a finite source configuration, but rather a closed configuration. And it indeed was one machine, and it took 3 days to get it. So, and we were stunned ourselves, and we were really surprised about the KMTnet data part of it.
Great. Well, that's exciting. Let's thank Marcus again. For the final talk of the session, it's my pleasure to introduce one of our local hosts. This is Dan Foreman-Mackey at the Center for Computational Astrophysics, and he's going to talk about using machine learning and statistics in the context of astronomy. So thank you, Dan.
All right. Thank you very much. It's been very fun to be here. I hope you are all having fun here at Flatiron. This is my title that I came up with, and I wanted to start with a couple of disclaimers. And the first one is this point that I don't really know anything about microlensing, so I hope that what I say is useful. I've tried, but hopefully I'll learn more. I'm especially excited about the hack session. And one word about the hack session: if you're participating in the hack session and haven't put a slide in the introductions deck, please go and do that right now. You don't need to pay attention to my talk. The other thing that I wanted to have as a disclaimer right at the beginning is that this is not a talk about machine learning, despite the title. And so if you really just wanted to hear about neural networks, then the coffee's probably ready outside. That being said, I did want to show this XKCD comic that Rachel showed earlier in the week after giving a shout out to my talk. And there will be a little bit of this character within this talk, even though it's not about machine learning. So time permitting, this is the outline of the talk that I'd like to give today. These are the two topics that I'd like to talk about. And the first one is the thing that I actually know most about, so I'll spend most of the time on that and then hopefully touch on the second part at the end. And so the two parts are, I'd like to talk about how you can use the sort of framework and infrastructure that's been developed as part of machine learning to improve the types of data analysis that you do already. And then the second part is sort of something that sort of a step beyond that. And in particular, I'm going to touch on a lot of things that Eric talked about yesterday in his talk, but sort of focus on a few specific points that he went through very quickly. So hopefully this is a complement to that. So when I talk about data analysis, this is the entire story, I would say. This is all of science. At some level, what you want to do is you want to take some data and you want to say what that data says about your physics. And you generally want to write down some mathematical function that describes this relationship right here. And then you would put that into an optimizer to try to maximize that to get sort of the best fit parameters for your physics. Or you might want to sample. And a key point about this right here that I think is especially true in microlensing from what I've been hearing this week is that there's a lot that goes into that bar right there. There's a lot of complicated physics and expensive numerical algorithms and all sorts of, there's a lot that goes in there. And we'll come back to that a little later. So I think, these are sort of the standard problems in all of data analysis, and I think these also are true in the context of microlensing. In general, your model, because there's so much code inside that bar, is computationally expensive to evaluate. And then you want to fit for your parameters, and so that involves evaluating your model, your computationally expensive model, many times. And even worse, there are all sorts of degeneracies and other problems that make fitting very hard. I'm just going to use fitting and inference interchangeably when I talk here today. And so here are some examples for why fitting might be hard. You might have a lot of parameters, and that's something I'm going to talk about today. And in particular, when I say parameters, they're the physical parameters that you care about, but there are often lots of nuisance parameters as well. So lots of other things that you don't understand about the data or that you have to model somehow, you have to parameterize somehow that you need to take into account. You might have large data sets. You might have lots of different data sets that you want to analyze. And then also something that's very familiar to people in this room, you might have strong covariances or multiple modes. And I'm going to talk about some ideas for how to tackle some of these problems. But basically, your goal at the end of the day is you want to minimize the number of function evaluation, the number of times you have to evaluate your computationally expensive model, but still getting good inferences. That's that's everyone's goal. And I'm going to talk about some ideas about how you might be able to do that using tools from machine learning. The answer, as far as I'm concerned these days, is derivatives. And when I say derivatives here, what I mean is we have this function. This actually isn't the same function. I realized this as I was going through my slides this morning. This is the likelihood function, but whatever. This is normally the computationally expensive part of your model. But you want to compute the derivative of this function with respect to the model. So these are the derivatives that I'm talking about. And in many cases, you can get huge computational advantages if you can take advantage of knowing what the derivative is with respect to the model parameters. And one thing I'd like to remind you is that there's a lot of complicated stuff that goes on in this bar, and I'm saying that we want to take the derivative of all of these things. And so, you know, that could be a pain. So here's an example. So I said I don't know about microlensing, but I didn't say what I do know about. I mostly work on transiting planets. And here's an example that Rodrigo Luger made as part of his STARRY project for computing the models that we need for transit light curves. And here I have an example of a model for a transiting planet. And here are some of the derivatives that I would be interested in computing, you know, with respect to all the physical parameters of my system. So those are some examples of the things that I would want to compute. Of course, there are other things, you know, there are noise models and things like that. And also, you might, or I might, disagree with some of the parameterizations that he chose. I might want to actually take the derivatives with respect to different parameters and things like that. So you can imagine that sort of even going through and just computing the derivatives once might not be the solution. So I asserted that derivatives are going to be important, but I just wanted to mention a few examples for why. And one is that I said that the things that you want to do are optimize or sample most of the time. And in most cases, the sort of state-of-the-art algorithms for optimizing a function actually require computing the derivatives of your objective function. And in many cases, probably when I don't know if this is true, but a lot of the time when people optimize their functions in astronomy, they use numerical estimates of what those derivatives are because it's easier to take tiny steps and estimate the derivative numerically. But that's actually very slow and noisy. So even if you do that, you're evaluating your function more times than you think you have, than you might expect, because each step is actually not a very good step. And so if you can find a way to get the analytic derivatives, then you'll get much better performance and greatly reduce the number of steps you have to do. Then also something that Eric talked about yesterday, just very briefly, was that for large dimensional problems, when you have more than about 10 parameters, the sort of state-of-the-art methods for doing MCMC also take advantage of gradients. And so that's something that I'm going to come back to in just a second, because that's kind of what I want to focus on. And this is especially true as the number of parameters gets larger. So here's my super scientific plot that describes this. I have along the x-axis the number of parameters that you have and how hard your inference is, or how much patience you need for your MCMC to converge. And if you use something like MC, which is the package that I wrote that's quite popular in astronomy, this is more or less what the scaling looks like. It gets really very painful, even if you have a lot of computers. And we'd really rather things look a little bit like this. I'm willing to work a little bit harder if I have lots of parameters, but it shouldn't be something ridiculous like that. And you can get this if you use derivatives and if you use gradient-based sampling methods. So let's just take 1 second to talk about MCMC. How many people in this room have used MCMC before? Yeah, okay, great. So this will probably be pretty familiar. Here I'm plotting log probability contours, and I want to draw samples from this space. And when you run MCMC, you get something like this, where you start somewhere in parameter space and you walk around and you accept and reject samples as you go through. And the key point is that your acceptance probability, schematically, only depends on the ratio of the log probabilities at each point. And so if you go to points in parameter space that have equal probability, then you're always going to accept that. Your acceptance probability would be 1. There are lots of reasons why that's awesome, but this is basically the way MCMC works. And when you use MCMC, you want to accept as many proposals as possible, but also try to move through the entire parameter space. And so sometime in like the 70s or early 80s, folks realized that if you draw a log probability, which kind of looks something like this, and then multiply it by -1, it looks an awful lot like a potential energy. And we're all physicists, so when we have a potential energy, we want to put a little ball in our potential, give it a little kick, and we know how to integrate that. And in particular, we would have some Hamiltonian that looks like that. We have our parameter, and we give it some momentum, and you integrate it through this potential. And that's my 1-second introduction to Hamiltonian Monte Carlo. And basically, the idea is that the Hamiltonian the potential energy in your Hamiltonian will be your minus log probability. And if you can integrate your particle and conserve energy, then every proposal, as your proposal for the MCMC, every proposal will be accepted if you conserve energy. So you'll move far, and you'll accept every step. So it's sort of the dream. This is the MCMC dream. That's why most people use this kind of thing now in other fields. But if any of us have ever integrated new systems like this, we also know that to do that numerically, you need to know the derivatives of your log probability, or of your potential, rather. And so that's why we need to know derivatives. So this is sort of my sketch of Hamiltonian Monte Carlo. In practice, people don't tend to use Hamiltonian Monte Carlo anymore. They use something called nuts, or generalizations of that, and that's implemented some other places. But this is the basic idea. So, okay. I said this requires derivatives, and remember, these are the derivatives that we're talking about. And I mentioned that we might want to reparameterize things. And Eric mentioned yesterday that these methods can be a little finicky, and they're very sensitive to the parameterizations. And so in the end, you actually will reparameterize many, many times. So actually going through and by hand computing all of the derivatives all the time is really not what you want to spend your life doing, I don't think. And so that brings me to the first bullet point in my talk, which is how we might be able to use tools from machine learning to take advantage of methods like this. So here's an example of a tool from machine learning. It's called TensorFlow. It's marketed as a machine learning framework for everyone, but I went in and fixed their website. It's actually much more general than that. It's a model building framework for everybody. Basically, machine learning is just it's just a fancy name for building models and fitting them to data. And so all of the technology that's built into TensorFlow can be used by us to build our models as well. And some of the things that you get if you use a library like that is you get fast linear algebra. That's specifically what it was designed to do. You can easily change parameterizations and things like that. It has built-in support for GPUs. And most important for my talk, it also gives you access to the derivatives of your objective function with respect to the parameters. So the real answer and the real reason why this works is something called autodiff, which is sort of the key word that I wanted to give for this part of the talk. And autodiff stands for automatic differentiation. And I just wanted to sketch very quickly what that's all about. So here is an example of a computer program. Right here, you have some inputs, and they give you some output. And this has all of your physical model in it and that kind of stuff. But you could rewrite when you write your computer program, you don't write it as a single line like this. It's many lines of code with specific operations at each line. So my schematic could be expanded like this. You pass your inputs through all sorts of different functions, and at the end of the day, you get out your output. Now, if you write it like this, then you might remember from high school that you can apply the chain rule to something like this and rewrite your derivative this way, schematically. And this is basically the whole idea of autodiff. The idea is that your code is just a set of operations that we know how to take the derivative of, so we can just automatically apply the chain rule to the code and write a separate function, a second function, that knows how to compute the derivative of your code. It's as easy as that. It sounds a little, it doesn't sound like it would be very efficient, things like that. But it definitely does work. That's why I'm talking about it. And we've used it a few times in astronomy, and other people have too. But the reason why it works, I wanted to bring up, is because autodiff in machine learning is called backpropagation, because in machine learning they love to come up with fancy names for things that have normal names other places. It's also called the chain rule. Anyways, but an important fact about this branding is that lots of companies like Google that supports TensorFlow, they make a lot of money because of these things. So they invest a lot of money into making sure that these things work really well and are super efficient. So we can take advantage of the fact that that there's been all of this investment to use these things in our work. So I just wanted to give a quick example of this in practice. How many people here use Python? There's been some. Okay, so this will be especially interesting to you. Here's a snippet of Python code. This is just doing linear regression and using NumPy. And I just wanted to show how you would do the same thing in TensorFlow to show that it's not too terribly different. This is the version in TensorFlow. I think I can go back. Maybe not. Oh yeah, there it is. So you see, the syntax is a little different, but more or less it's the same. So as long as your code looks, if you have code written in NumPy, then actually transitioning to one of these other frameworks that can take derivatives is actually quite easy. Okay, but I've been talking about TensorFlow, but in Python alone, there are at least 10 different libraries that implement this kind of thing. And then also in other languages, there are, if you use C or Fortran or C++ or Julia or whatever, there's sort of a whole set of different options in these languages. And so there seemed like there was lots of interest in Python in this room, and I mostly know about Python, so I'll just mention that here, but I'm happy to chat offline about other options if you're using a different language. And Rodrigo Luger at the back knows a lot about the C++ options. So TensorFlow, like I mentioned, is one popular example, and it has features for doing inference in a part called TensorFlow probability. All the cool kids are using PyTorch now, apparently. And there's a library called Pyro for doing inference with PyTorch. There's also PyMZ3, which is an inference library built on top of Theano, which is another model building language. And then there's Stan, which is sort of the gold standard for Hamiltonian Monte Carlo type methods. And all of these are accessible from Python. These are just some of the examples that are possible. And when you're choosing, I would say you should think about the sort of inference capabilities that are built in. So it's nice to not have to implement your own no U-turn sampler, because I've tried and it's really annoying. But it's also worth thinking about extensibility, because if your code isn't just a set of NumPy functions, and you have clever ways of solving some subproblem, it's very useful to be able to provide your own derivatives for those parts of the problem. I'm not going to talk about that, but I think that's crucially important in astronomy applications. So I just wanted to give a quick example where we've used this. So Megan Bedell, who's a postdoc here, recently published a paper where she used TensorFlow. The paper is called Wobbly, and we were doing extreme precision radial velocity measurements. And here we used TensorFlow as our modeling language, and we had to extend it. TensorFlow didn't have interpolation built in, for example, so we had to implement that, but it was easy to do. And basically, the reason why we had to do this is we were building a model that, that sort of has these different components that look like the colored lines at the top here. The details aren't too important, but basically our model was just the value of the stellar flux at just tiny points all the way along this line. So we have, hundreds of thousands of parameters in our model, and we want to fit for all of those parameters. And by implementing this inside of TensorFlow, we were able to optimize this model, even though it had outrageous numbers of parameters, all very efficiently. And so this is one example. In a project that I'm very excited about, I actually chose to use PyMC3 as my modeling language. And the reason for that is that it sort of is the most feature-rich Python library for doing gradient-based inference in Python. And I recently released this as a project called Exoplanet. I got pip install Exoplanet, which was pretty sweet. And so this does a lot of transit fitting, radial velocity fitting, and that kind of stuff built on previous work in using all of the derivative information. But and I'd love to hack this over the next couple of days on seeing how this could be applied in a microlensing context. But specifically of interest, there are a lot of examples that aren't necessarily specific to this package about how to use this type of thing in an astronomical context. And I've tried to write it in language that might be familiar to people here. In particular, things like scalable Gaussian process regression using derivatives and things like that. So that might come in handy for some of the people here. And yes, I'd love to hack on this over the next couple of days. Okay, so I have just a few minutes left, so I wanted to touch on this second bullet point right here. And the idea is that, and I think, anyways, I have another disclaimer for this part. I don't really have any idea what I'm talking about in this part. That's sort of been the theme of this talk, I guess. But it seems like they could be really relevant, and I'd be really excited to chat with people who are interested in trying out this kind of thing in a microlensing setting over the next couple of days. So here we have the usual things. We have a computationally expensive model, but the key point is that it might also be badly behaved, so multiple modes, things like that. And the idea is to turn on the machine learning to try to improve this kind of thing. So instead of actually using machine learning tools to take derivatives of your model, to actually use machine learning models as a tool in the process. And in particular, you might want to use machine learning to try to approximate your log probability surface or some part of your model. And I think this is very promising because you might be able to come up with a good model with a small number of evaluations of your model, of your actual physical model. And it might also help you choose where the best place is to evaluate, to run your full model as well. So the sort of key word from the literature for this kind of thing is Bayesian optimization. It's a terrible name. There's really nothing Bayesian about it. I'm happy to chat offline about where this comes from, but this would be the kind of thing to search for. This is the key word. And I just wanted to show a quick demo of how this might work in a very simple context. So here I have this blue line right here, which is a function that I'm trying to find the minimum of. It's lightly multimodal and things like that to try to give a sense of what we can do. You can see this example at this URL down here. It's a tutorial on my George package. And basically the idea is that you start by evaluating your model at a few random places, and then you try to approximate what your what your objective is, just using those points. And here I don't know if you can see the gray bar, but this is my estimate and its uncertainty for what the value of this blue line is. And it's pretty crap right now. But you look at this, you use this estimate to work out what is your gain in information for evaluating a new point somewhere along this line. And that gain in information would be quantified by this green line right here. And you would choose to evaluate your model again somewhere where that's high. So here it's up over there. And then you improve your estimate for the model, and you iterate this a few times. And you'll see that we very quickly find the mode that we're looking for right here. And we've optimized our function with only 10 model evaluations, and we didn't get stuck in this local minimum. And so here, like I said, I used a Gaussian process to do that estimate, and that's sort of standard in this field. And Gaussian processes might be more familiar to people in this room, but really, you know, in some sense, they are tools from machine learning. And you could imagine swapping out something like a neural network or something like that, if that's what you're in the mood for, as the layer that you put in the prediction there. And there's a lot of literature about this that I'd be happy to chat about. There are also some examples where you can use things like this inside of a sampling loop, so to do MCMC or something like that in this context. So like I said, I don't have a lot to say about this particular topic, but I would be very excited to try hacking on something like this over the next couple of days as well. So here were the sort of two topics that I wanted to touch on today. Get some keywords for hacking. Here are some of the keywords that might be of relevance from what I've talked about here. And on that note, I'd just like to say I'm looking forward to the hacking, and I'm looking forward to chatting with everyone about these methods and other data analysis methods over the next couple of days. Thank you very much.
Great. Questions for Dan? Jonas, say your hand first.
I have two questions. The first one is, you talked about when we should be using machine learning and the benefits of using machine learning. Can you tell us when we should not be using machine learning? When is it an overkill to use machine learning?
Yeah, sure. I mean, this is it's a good question. I mean, I think this is an interesting topic for a longer discussion. Yeah. I would say that in general, in astrophysics, machine learning is especially useful when you can use it as a tool to describe a part of your problem that you don't necessarily care about the interpretation of so much. And so in this case, if you can use it as an intermediate layer to try to estimate the function, or to try to speed up your calculations, if you're using it as a tool, then that's what it's designed for. But I think if I don't think that this gets rid of the need for understanding, the fast physics models, and because if you actually want to understand the physics of what's going on, you still want to make sure that you use the correct physical model in there. So I think figuring out where that line should be drawn is the key question. Okay. And I'd love to chat about it more later.
And I have a second question. Sorry, Kevin. So my second question is very quickly. In microlensing light curves, there are a lot of discontinuities. Right? When so how do you think that's going to impact the machine learning methods?
Yeah, absolutely. So I don't know the answer to that really. I expect that the things like the derivatives that I was talking about at the beginning, that will be especially useful. I think Eric broke it down into explore and exploit yesterday. And using derivatives in the explore phase could be very useful because it can help you, it can reduce the number of optimization steps you need to do if you're sort of trying out different parts of parameter space and things like that. I don't know the details of how this is going to all play out, but I'm excited to see.
Dave, and then
Scott. Well, in doing binary lens modeling and then later triple lens modeling, I abandoned using derivatives a long time ago. And the reason was that I found it's far more important to deal with the changing correlations between the parameters. And so, to the extent that my system is successful, it's because it's changing parameters very regularly, and this is really important in sort of the explore phase because you're going down valleys in chi-squared space and always making turns here and there. It's not clear to me that that using derivatives now would help very much. But on the other hand, I haven't looked at it for a long time.
Sure. Yeah. So just a quick thing to say about that is that in the context of sampling using derivatives, you also have to tune the covariances. So you would still benefit from all the work that you've done, understanding how the different parameters vary together and things like, all of that would still be a crucial part of this. This would just increase the efficiency of whatever sampling algorithm you're using or whatever optimization algorithm you're using as a step beyond what you already have. I think it's worth considering. But yeah, definitely both of those components are crucial.
Yeah, well, I guess I was wondering if there's any examples for which that you know of where calculating derivatives, if you have to do it, very, very often, then at some point it's just easier not to do it.
So the cool thing about these auto-diff methods that I was talking about is that you actually I'd be happy to chat on the board some more about the details about this, but you actually get the derivative with respect to all of your parameters for the cost of within about a factor of 2 to 4 of just evaluating the function once.
So, can you go back to your plot of the derivatives of the transit?
Sure.
So I've worked in microlensing transits, radial velocities, and I don't know if this is just me being naive or what, but my experience with transits and radial velocities is that they're much more well behaved in terms of the correlation or the correspondence between the observables and the parameters.
Yep.
And therefore, taking derivatives is much more useful. In fact, I thought it was interesting. The derivatives you showed are not actually the derivatives you want, because they aren't. What you really want to do is take the derivatives of the observables, which are like the full width half max, and you can see that these are not the derivatives you want because they're highly correlated in many cases, right? Whereas you can come up with a set of roughly 5 parameters that are almost uncorrelated, right? We showed this in Carter et al. If you use derivatives. If we tried to do this with microlensing, right? And then these derivatives are really pretty tame, right? If you look at them. If you try to do this with microlensing and you take a derivative with respect to Q and you step at 10 to the minus 5, right? You get a spike that's enormous, right? And this is where I think derivatives start becoming very problematic. And I think it's my experience is from fitting transits, radial velocities in microlensing, is that in microlensing, because these derivatives are so spiky and poorly behaved and et cetera, with respect to the canonical parameters, that derivatives are sometimes don't seem like they're very useful. And I think this is sort of what Dave was saying. Now, Eric did mention that you could come up with a basis set of functions, and we have done this before, like for binary lens events, we'd use the time of the Costa crossings, but there you have to sort of think about it and figure out what those parameters should be that are going to have smooth derivatives with respect to the observables.
Yeah. So just a few things to say. So first of all, just to reiterate, this definitely doesn't get rid of reparameterization questions and things. So in practice, these are for display purposes only. These are not the derivatives that we calculate. And more specifically, we calculate the derivatives with respect to the log probability, not with respect to the light curve. And so there are various things related to that. But yeah, for sure, reparameterization makes a big difference. And in the context of transit fitting, one example is the period of the transit. It's so well constrained compared to the other thing, that there were some issues at the beginning with actually taking advantage of the derivatives in that space. And this comes back to what Dave was saying, or what I was saying to Dave, which is that you also benefit from tuning the scales of the problem and things like that. So this doesn't get rid of those kinds of things, but I would say that in the context of transit fitting, this increases the efficiency of our samplers by many orders of magnitude. I can fit a multi-planet test system on my laptop in an hour and a half using all 20,000 data points and a Gaussian process and like all those things, which traditionally would take months on a computer cluster. So I don't think it. I think that you have to think about both sides of that. But I think this could benefit.
So I think in the interest of preserving our coffee break, we should end questions there. Dan is here. He's local. He said let's hack. So there can be a lot of fruitful discussion in the breaks. So let's thank all of our speakers again.